Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the director of content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Rolang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
First of all, a round of thanks to everyone, especially to you, Derek, for hosting and editing and just making sure the community has access to this material. It's a great service. I really appreciate it. And also thanks to Christian and to Isaac. Today we're just going to have some fun. I wanted to talk about a theory that could be used to inform some stuff that we do on RChain, but it has a wider range of applications. So I call it TOGL, and it's an algebraic way to think about graphs. Another way to think about it for programmers it's a data type for graphs. If you go and look at the graph theory, a whole bunch of graph theory is done in terms of presentations of graphs as essentially nodes and edges, collections of vertices and collections of edges. And that doesn't really speak to the way that graphs naturally form or the way that we use graphs in the computational setting. There is a different way to formulate them as a data type, which is as a recursive algebraic data type. And the analogy I want to emphasize is the way we think about the list data type. So if you were going to write down the list data type as a domain equation, then it would be, a functor, which takes some type A as an argument, and then produces the sum, which is either 1 or A cross list A. So you can think of that as a cons representation, right? So you have either the empty list or you cons a value onto the rest of the list. And that's clearly a recursive presentation, and it lines up with our way of thinking about lists, but it has other advantages. And a nodes and edges presentation of graphs does not have that style. It doesn't have that sort of flavor of presentation. And as a result, when you try to write algorithms for graphs or even express graphs themselves, it can't take advantage of this kind of recursive structure. And so there's a lot more complexity that these algorithms have to sort of wade through. And I think a lot of this complexity is needless. But in order to walk through it, I want to kind of go through the construction carefully. There's some nice visualizations for it, and I'll make those visualizations available for the website, the podcast. We can talk about them, but it also I think it lends itself pretty nicely to an English description. But let me stop there and just check in and see if what I'm saying makes sense to Isaac and Christian.
Yeah, this sounds like a good motivation. Just incorporate a better theory of the stuff that actually is the reason for the graph rather than just seeing it as an external mathematical structure from the beginning.
In terms of the presentation, I'm using a style that's known to type theorists and proof theorists, but maybe not so well known amongst programmers. So I have this idea of a well-formed graph, and I give a sequent theory and a proof theory to form graphs and then determine when graphs are well-formed. So you can prove when someone hands you a graph whether it's a well-formed graph. So we start with this idea that we're going to have this domain of graphs, which is parametric in two things. One is a universe from which we draw our vertices, and the other is a universe from which we draw some variables. And the variables are important because we want to be able to let variables stand for vertices in graphs. And there's a wider construction in which we have another class of variables which would stand for whole graphs. But let's begin simply, and then move to sort of more complicated structures. So we have this domain of graphs that's going to be formed from a type for variables and a type for vertices. And then we have a notion of gamma, which is the list of variables that are utilized in the formation of the graph. And then we can form a sequent, which is given this list, we want to formulate a graph over that list of variable references. So I use the turnstile notation, and we can read it as thinks that. So we have given some gamma, which is this list of variable references, thinks that G is well formed. So that's a way to turn the sequent notation into an English sentence. And the general shape of the formation rules are going to be of the form, given in different sequence, which determine that G1 through Gn are in fact well formed. Then we can combine the dependencies of each of the sequence, and that combination of dependencies thinks that some way of combining the graphs is also well formed. So if you have some graph constructor or CTOR K, then you're going to form this K over the graphs, and you're going to form a similar kind of K over the sequence. So it says how you combine the dependency lists to get a combined graph that is well formed. So that sounds somewhat abstract, but we'll give some good examples in just a minute. So just building up carefully. So we're going to say that as long as you draw a vertex from a universe of vertexes, any gamma thinks that the vertex is well formed. Likewise, if you draw a variable from the universe of variables, then gamma that mentions x will think that x is well formed. And then we have a notion of well-formed graph. So we sort of are building up recursively. And like I said, our gammas are just sequences of variables. And then we have a collection of graph expressions. There's just a few of them. The way I've done it in this notation is we've got a zero graph, or the empty graph. If you had a graph G, then if you wrote vertex in parallel or pipe G, that's adding a vertex V to the graph G. And then we can, if you had two graphs, say G and H, then we could combine them with a tensor. So just basically lay them side by side, and that gives you a new graph. Perhaps one of the things that's most distinct in this approach is nominating a particular vertex with a variable. So this is a let expression. So we would say let x, which is a variable, equal v in some g. And the reason we want to do that is because we want to be able to form edges, but we only ever form edges between variables. So this let thing actually picks out a vertex and gives it a name. And then if you have two let expressions, then you can form an edge between the two. That's the total set of graph expressions. So I have a stack edit document that documents all this. There's actually a more recent write-up, but I couldn't find the link to that one. So this one is a little bit older than the more recent write-up, but it's still pretty good in terms of getting the ideas across. I actually give English language pronunciation, so you have 0 is the empty graph or just empty. And then the pipe construction is a join V to G. And the tensor construction is juxtapose G1 and G2 or G and H. And the let expression is just, let X be V and G. And then the edge construction is connect G1 to G2 with an edge from X1 to X2. So that's where you've got this pairing, let X1 equal V1 and G1 with let X2 equal V2 and G2. So that's the formal expression, and we pronounce it connect G1 to G2 with an edge from X1 to X2. So in that way, the edges are anonymous, but you can also provide a name for them as well. But just for purposes of discussion, we start off with the anonymous or unnamed edges. Let me stop there and just check in with Isaac and Christian. Is this making sense?
Yeah, it's making sense. Yeah, that was kind of my first question, was when you declare this edge, is it just an existence, or can it hold some structure?
You can allow it to hold structure. I'm building the theory in pieces or iteratively. Yeah.
Okay.
So we've talked about the structure of the sequence, and now we're going to talk about the structure of the proofs. And the proofs are basically what allow you to guarantee that a graph is well formed. So the foundation of the whole thing is that if you have no dependencies, then 0 is well founded. And if little v is in the universe of variables, then the empty dependency list gives you the vertex is well founded, and there's a similar rule for variation. So there's a rule which we call participation, which says if you have some sequence that says that G is well founded, and you know that V is a legal vertex, then you can adjoin the vertex to the graph, and that gives you a well-founded graph where the dependency list is just the dependency list from the formation of the graph. Correspondingly, there's a similar rule for adjoining a variable to a graph. So you can adjoin a variable, remembering that ultimately, for this to make sense, there has to be a let expression which would bind the variable to the graph.
Are those slashes just for spacing?
Yeah, I think what happened was there was somehow some semicolons got dropped. Those were supposed to be spacing slashes.
Okay.
If you have that gamma 1 thinks that G is well formed, and gamma 2 thinks that G2 is well formed, then if you just combine the two dependency lists, so gamma 1 comma gamma 2 thinks that G1 tensor G2 is well formed. And the assumption is there's a side condition that gamma 1 intersect with gamma 2 must be empty. So they can't share any variables.
And what's the reason for that?
So this is the meaning of tensor. Otherwise, they could potentially overlap in some way, right? So, yeah. And then we have nomination. So if you have a legal vertex and you have that gamma comma x thinks that G is well formed, then you can get that let x equal V in G is well formed. So notice that it's not a requirement that V actually occur in G. But in the case that it does, then you're binding something there. And then finally you have a connection. So if gamma 1 thinks that let x1 equal V1 and G1 is a well-formed graph, and gamma 2 thinks that let x2 equal V2 and G2 is well-formed, then you can form the graph that connects x1 to x2 in G1 and G2, or between G1 and G2. There's a set of English language interpretations of that in the document, but that sort of gives you a sense of how we give proof rules that are going to determine that you have created a graph. We just went through the graph formation rules.
Okay.
So I'm kind of hoping that you'll express some reservations or questions, because there should be some natural equations. So for example, we want to equate G1 tensor G2 with G2 tensor G1. That should happen. And then we should have some rules about let. If you iterate let over the same variable, then it should only be the outer variable that the other, in other words, there's a kind of shadowing that happens, right?
Yeah.
So you have to collapse that. You can calculate membership. Now this is where the other write-up is a little better. So you can calculate membership. You can ask whether or not V is in a particular graph. So for example, you know that V is in the adjoining of V to G. You know that if V is in G, then V will necessarily be in G tensor G prime. You know that if V is in G, then V will be in let X equal V in G. And similarly for edges, now you'll have a link 1 and a link 2. So you can calculate membership in this way. And with the notion of membership, you can actually characterize those equations. So for example, if you tensor the empty graph with a graph, it should just be the same as the graph. If you tensor G1 with G2, it should be the same as G2 with G1. If you tensor G1 with G1 tensor G2, that should be the same as G1 tensor G2 tensor G3, so it's associative. You should be able to permute the adjoining of any vertices, and you should be able to collapse nested lets in the case that they mention the same vertex, and likewise with variables. And then there's a form of extrusion. So if you nominate a vertex with a variable, so you select it and name it, and then you tensor that with some graph, then you should be able to pull the tensor inside the nomination. That's kind of important. So there are all kinds of things that are simplified because of this presentation. So there are lots of things that you can do now with subgraph isomorphism that are not NP hard because of the way we've formed the graphs. But there's no such thing as a free lunch, and so the complexity moves over into checking these equalities, right? So in particular, checking that something decomposes into a tensor of two graphs can be exceptionally hard. So that's where the complexity moves over.
A quick question.
Yeah.
I was expecting some rules that if G1 equals G2, then when you apply any of the constructors onto them, those are equal, so that you can apply locally.
Yeah. So those are theorems rather than rules. Yeah. You can prove those. The only place where you have to worry is in variable binding.
Okay.
The tensor stuff is a straightforward proof. The adjoining stuff is a straightforward proof. Edge formation is a straightforward proof. It's only in the variable binding stuff where you have to be a little more careful. You have to quantify over certain substitutions.
Yep.
Let me now talk about some examples. So there's kind of a family of examples starting from the discrete graph, right? So all the nodes are discrete. And then you form a chain. So you have one node connected to the next node, connected to a next node, right? So basically like a pencil or a chain, right? So that's the next level of complexity. And then you want to be able to form a cycle, and then you'd like to be able to form a complete graph. So those are sort of some standard examples from graph theory. Mm-hmm. And if you look at each of these examples in terms of your favorite graph data type, it's really interesting to see that how the complexity changes as the complexity of the example changes, right? So essentially the complexity of the examples are getting greater and greater and greater until finally you get to the complete graph, and the complexity of the object is very high. And the question is, what happens to the complexity of the representation as the complexity of the graph goes up? And what distinguishes this theory from other graph representations is that essentially the complexity of the representation stays almost constant. So we get the one-liner descriptions of the graphs that remain one-liners as the complexity of the graph goes up. And that these one-liner descriptions don't change very much. which means that there's something right about this kind of formulation, and that's what makes this interesting. The way I describe these is I describe these graphs in terms of morphisms from some other domain. So, for example, the natural numbers into the domain of graphs. So the discrete graph on the natural number 0 is just the empty graph. And then the discrete graph on n is going to be equal to a join n, whatever that is. So we're going to take the naturals as our universe of vertices. So the discrete graph on n, a join to 0, tensor with the discrete graph on n minus 1. And then if we introduce this notation of sort of box n as a join n to 0, or put n in square braces, we can see that, discrete n is just box n tensor box n minus 1 tensor yada 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 all the way down to 0. So it's a nice, crisp, recursive specification of the graph that has a natural expansion that looks algebraically just like the graph looks if you were to draw the graph. And now the interesting thing is we can use the idea of the discrete graph to make a chain. I'm doing something a little tricky, which is I'm building variables out of the domain of vertices. So, and the way I distinguish them is with quotes. We have variables that are essentially the quotes of natural numbers. The chain of 0 is just the empty graph. The chain of 1 is to let the quote 2 be the vertex 1 in box 1. That box 1 stands for adjoining 1 to the empty graph. And then chain n is let 2n, the quote 2n equal n in let 2n minus 1 equal refer to n in box n, and then chain of n minus 1. And notice that what that's doing is always chain of n unless it's 0 is a let form. Right? And since we spell out exactly what chain of 1 is, we'll bottom out at 1. So you can verify that for any n greater than or equal to 1, chain of n is going to be a let form or a nominated form. So then this idea of chain of n is going to be an edge, it's got the right shape.
Are these quotes supposed to be suggestive of row quotes?
They are. We'll get to that later. Right now I'm just making things easy on us. Yeah. Right? So that I don't have to manage subscripts on variables. Right? That's what I'd have to do in order to express this in another way. Once you can adduce this little lemma that I made, then it's easy to see that the chain form gives you exactly the chain graph that I mentioned. And now, once you've got that, then the cycle is even easier. The cycle of no nodes is just the empty graph. And then the cycle of n nodes is, well, you take the chain of n, and then you adjoin the end of it to the beginning. Yeah, you pick out the 1 and you adjoin it to the beginning. So again, so notice what's happened, right? So the complexity of the discrete graph is a single line recursive function. The complexity of the chain is a 2-line recursive function. The complexity of the cycle is a 2-line recursive function. The complete graph requires the introduction of the notion of a forecomprehension and the ability to go and pick out the entire vertex set. And then we can lift the edge computation from 2 nominated graphs, or graphs in the nominated form, to an edge formation over 2 forecomprehensions. So basically it's connecting everything in one forecomprehension to connecting everything in the other forecomprehension. We're introducing a little bit of syntax that has a very intuitive meaning for programmers. And the syntax is basically just like a Scala forecomprehension or a row line forecomprehension. So for x from the vertex set of G. If some predicate on X holds, then you yield a particular graph. That's the expression. If we have two of those expressions, that's going to yield, if you expand it out, a bunch of lead expressions, which could then be used to formulate an edge. And so this gives you a collection of nominated expressions cross basically a Cartesian product of two nominated expressions, and then you can form all edges between all the pairs. No surprise, we can form the complete graph just by so the complete graph. So again, it's a single recursive equation or pair of recursive equations. The complete graph of 0 is the empty graph, and then if you have n, well, you go and form the complete graph of n minus 1, and then you adjoin a vertex. You make a graph that basically just has one vertex, and then you form all the edges from that vertex to all the others. That's how that's done. The complexity of the description remains basically constant. We did do this for comprehension trick, but I argue that it's a very natural computational device. For comprehension syntax has found its way into mathematics through set builder notation. So that's whatever it is, over 100 years old. And it first found its way in the mainstream computing community through SQL. So select from where is for comprehension syntax. And then it found its way again through the Haskell do notation and generators in languages like Python, and then was lifted again into the limelight in Scala with their for comprehension notation. So it's found its way into sort of mainstream mathematics and computing over and over and over again. It's a very, very natural thing to want to include, and mathematicians should feel very comfortable with this, as should computer scientists. In the presentation, we talk about wires and rewrite systems. So there's a natural way to encode the lambda calculus in this setting. And so, for example, Christian, in your work on graph-enriched semantics for formulae, you might consider this kind of notation as a way to calculate these enriched gadgets.
Yeah, that would be very nice.
So that was one of the reasons why I thought it would be interesting to have you on this call, is like, do you have a notation for these gadgets? And here is one. It turns out that you can also provide a theory of categories on top of this. The theory of categories that are built over a domain X and a domain V are subdomains of the theory of graphs, right? So there's extra information about how paths have to form arrows, form direct links, right? So there's always an arrow that reflects a path.
I didn't quite understand that.
A category is closed under composition, right? So if I take two edges in a graph and I consider the path, two edges where the target of one edge is the source of another, then I have to have an edge in my graph where the source of the first is the source of this new edge, and the target of the second is the target of the new edge.
Yeah.
And in fact, I have to do that for all paths.
Right. Yeah. So really, you're just saying we can take any category represented as a graph, but it's a particular type of graph because it has to have this composition rule.
That's exactly
within
right.
it. Yeah.
That's precisely what's going on. And then one of the interesting things is that because we can do this kind of decoration stuff on edges, we can actually give a formation of n categories using this approach. So I kind of sketched this out for Mike and some others in Park City in Utah a couple of years ago, but I didn't write it up here. If you're ever interested, Christian, I can go through that construction.
Yeah.
But what I wanted to do here to sort of talk about why this is really starts to get very interesting since we're parametric in X and V, we can do all kinds of weird recursion things, right? So I can make this new domain, say D of X and V, which is G of X plus D of X and V together with V plus D of XV. Now you've got the variables mention this domain and the vertices mention this domain. We get to compute graphs that talk about themselves, which is really kind of interesting. So you can take any graph and form the graph of its syntax.
Wow.
And which I think is kind of fun. You get graphs that mention other graphs, that talk about other graphs. And I think that has a lot of obvious power. That's one thing. But then the other thing that's really interesting is that we can form a type system. So we can use the ladle construction. If we take our collection as just sets, as opposed to multi-sets or some other commutative monoid, our formulae would then range over true, which is our ground, and then the usual Boolean constructions. So if phi and c are formulae, then you can form the conjunctions of phi and c. And then if we don't talk about negation yet, we can have zero. So it's the logical lifting of the empty graph to the logical formula that picks out all graphs that are structurally equivalent to the empty graph. And then we can form a formula, which, given a formula phi, we can adjoin a vertex to that formula, right? So this would pick out all graphs that have that vertex adjoined. We can form let x equal v in phi, so it picks out all the graphs that have this nomination as an outer layer. And then we can do the same thing for connection. I can connect the set of graphs phi, or that satisfy phi, to the set of graphs that satisfy c through x1 and x2, nominating, or naming the vertices v1 and v2. And then, intriguingly, right, if you have internal structure on your vertices or your variables, then you can extend like we do in this reflective domain D. Then you can utilize that structure in your formulae, right? So you can also impose, rather than just having your formulae specifically mention V's and X's, you could have formulae for V's and X's that exploit their internal structure. So you can add additional stuff. And so this is an extremely compact logical language for characterizing graphs.
Yeah.
There are two different ways to kind of form types of graphs. One are sort of these natural subdomains of G, like the category subdomain of G is a type. And then there's this question about whether or not the types that we get from the formulae line up with those domains. I have a conjecture here that talk about the relationship of those two different types. But, sort of as a teaser, I'll not mention exactly what that conjecture is, but suggest that people go check out the write-up.
Which two types was that?
So notice that we can kind of pick out subdomains of a particular domain of graphs, right?
Yeah.
Like C of XV is a subdomain of G of XV. And that's kind of a native notion of type, right? How do I programmatically or mathematically describe these subdomains? By hook or by crook, I get to use whatever mathematical gadgetry that would allow me to pick out a subdomain, right? But then there's this other way of picking out types, which are these formulae, this logical language that I've described, right? Right, and then the question is, what's the relationship between those two?
Yeah.
Like, how expressive are the formulae in terms of this sort of more native way of picking out subdomains?
I see.
And it turns out there's an interesting relationship between those two. And then I just want to mention that there are lots of different operations that can be provided just by manipulating the X and the V, right? So if I have a G that's built on an X and a V, I could flip their roles. Right? So I could make graphs that are where the vertices become the variables and the variables become the vertices.
Why would you want to do that?
There are any number of technical reasons that have to do with relationships about syntax. You could eliminate the variables. You could say, well, given a graph that is just that is built on X's and V's, only consider the graphs where V's are also the variables as well as the vertices. And similarly, build a domain of graphs where the variables are the vertices as well as the variables. And then you can do other kinds of things, like you could combine the domains. So if I have G built on X1 and V1, and I have G built on X2 and V2, I can do a summation where I have G built on X1 plus X2 and V1 plus V2. And I could do the same thing with the product, right? So I can take the product of the two. And then I can do interesting things like crossover, right? So I can do G of X1, V1, X2, V2. The variable part is X1 plus V1, and the vertex part is X2 plus V2. And there are lots of other operations like this. And you can utilize those in sort of Holland-style evolutionary processes to pick out graphs, which is particularly useful in a setting where you have reflection, like this D domain that I described before.
For these operations, would you need to be careful or have some theorems that you're still going to be able to make the kind of interpretations that you want, or that you're going to preserve subdomains or something as you? The
recommendation is that those are theorems.
Yeah.
And that you prove when you have natural homomorphisms. Right? And those homomorphisms will ultimately depend upon the internal structure of X and V.
Yeah.
Like if you've got a lot of rich structure in V and not so much rich structure in X, then flipping them around will not do very much.
Yeah.
Right. You won't be able to preserve a lot. You get maximum preservation when you do the reflective domain.
Yeah.
You've got this fractal-like gadget, right? And so if you flip it around, right, it doesn't matter so much. You've got the fixed point of all those operations. So you'll get maximal preservation like that. Part of the reason I'm taking this approach in terms of the discussion is I just want people to see that this formulation allows us to do this kind of design level thinking that I've been trying to promote over and over again. Like in this presentation of graphs, I've climbed the hill so fast. Like you don't see these kinds of operations available even in Diestel's algebraic graph theory. This kind of stuff is just not available. You can't see the forest for the trees in the nodes and edges formulation of graphs. Even Barr's presentation of graphs in sort of a categorical graph language doesn't have these kinds of constructions. And in particular, you don't get anything like Ladle, or in particular, this relationship between different ways of picking out subdomains and then being able to talk about what's representable via the logic and what's not. The point is that it gives you this design level thinking. It gives you a vantage point from which to be able to see much more of the landscape of graphs, or at least in my opinion. And I also wanted to point out that it's a sort of a natural outgrowth of a more modern way of thinking about graphs. So one comparison that I would recommend people go and take a look at is the notion of graph and graph logics that grew out of process calculi. So Luca Cardelli and Giorgio Gelli and Philippa Gardner came up with a kind of graph logic that was built out of two steps. The first step is looking at a natural encoding of graphs in process calculi. Right. So there's a natural way to think about graphs in process calculi that have to do with the prefixes in encoding edges. And that insight goes all the way back to Milner and Hennessy's insight with the Hennessy-Milner logic, right? So seeing the actions as giving you an edge between vertices, which are related to the process states, so the terms. So then that gives rise to an encoding in process calculi. And then when you have the spatial behavioral logics, those logics can now talk about processes that are natural representations of graphs. Gelly took this all the way to implementation. He implemented a graph query language based upon that logic that it has a pretty high expressive power. It's different than the one that I provided here in terms of ladle, but they have a similar expressive power, and you have roughly the same kind of complexity issues, right? If you try to decompose a graph as a tensor, then that's going to result in certain kinds of complexity. But there are so many more things you can say in this setting that you can't even say in the nodes and edges setting because it's computationally too overpowering.
This graph logic related to process calculi is definitely about like what I was going to ask in terms of like the very basic, concrete, everyday applications of this idea in the row calculus. Are you translating row terms into graphs that depict the communication channel relations between the processes that compose the terms?
What I was trying to do with this was to not tie myself to process calculi. This gives you a native notion of graph. And then you can go and think about, all the different kinds of graphs that you could build out of process calculi. And you could also think about all the different ways you might consider representing graphs in process calculi. And then you kind of can compare that representation to this representation.
A sort of related question, like if you are inputting some type as a dependency that has its own notion of rewriting, how do you transfer that implicit graph of terms and rewrites of that language into this? Is there a nice way to do that?
Yes, there is. So that's the example that I give for the lambda calculus.
Oh yeah.
There are a couple of different ways to do it. I gave one way. The graph of all reductions of a term is given by the red formula in the theory of graphs document. There are probably other ways to do this that are even more friendly, but I've got basically 4 equations that give the entire graph. So it feels relatively tractable. In the document, I invite the ambitious reader to go and give a red formulation for the row calculus.
Yeah.
And it's easier to do it for row than for pi, but just because you have fewer moving parts in row than you do in pi. But you could do something similar for pi or blue calculus or ambient calculus or what have you. One of the things that I felt was really encouraging is that if you take the standard graph theory examples, the notation scales. If you try to calculate the graph of reductions, the notation scales. If you try to represent categories, the notation scales. And then there's all this other stuff that the notation can do in a scalable fashion that is just not even approachable in ordinary graph theory, such as this syntactic domain, where we have this recursive thing, and I can now talk about the syntax of a graph in a graph, right? That's just not even considered or contemplated in graph theory, let alone in a way that a handful of recursive equations.
That was the part that you kind of flew through. I thought it was really cool, but I had trouble thinking about what it would even mean for a graph to be able to talk about its own syntax.
Yeah, sure. Well, fortunately, the math is there. Finally, we have this logical language that allows us to talk about sets of graphs or collections of graphs as formulae. So the point is that it feels exceptionally scalable, right? The dog doesn't bark, right? the curious incident of the dog in the night, right? The dog doesn't bark. There's the notation is quite happy and familiar and comfortable with this very wide range of examples, and doesn't break a sweat, doesn't get excited or overexerted, and we can cover lots and lots and lots of stuff. That's the idea, and it's one of these things where I just hope that someone out there will pick it up and run with it. Goodness gracious, it takes years to take even just a row calculus all the way to market. Like a very natural thing to do with it would be to try to build a competitor to some of the graph query or graph database things. Since this is so scalable, I suspect that it's far superior to the existing graph databases, but we'd have to prove that by doing an implementation.
So is like the main difference the idea of the dependencies?
That's exactly right. So it's the main difference is how you build edges. So in this approach, you only ever build edges between named vertices. And then you have to manage that naming technology. That's what the dependencies are doing. It's just applications of stuff we know and love from Lambda, right? Lambda tells us how to deal with variables. And so if you just inject that in this most natural way into the rest of the graph constructions, then you basically it's just a conservative extension of what you would expect from a completely naive data type to add variable management. That's how I arrived at this particular construction.